So good day everyone. So we are here on about the continuation of our previous lesson. So in our previous lesson, we study about the ideal Rankine cycle and we solved various parameters involved in a Rankine cycle. Here in our next chapter, our next lesson, we're going to discuss and to solve the methods to increase the Rankine cycle efficiency and the what we call the actual Rankine efficiency. So, what is the meaning of the actual Rankine efficiency? So, the actual Rankine efficiency is those right Rankine cycle na meron tayong mga accessories na. Ano ba yung sinatawag natin accessories? Yung mga accessories na yun yung inilalagay natin sa cycle efficiency para tumaas yung sa Rankine cycle para tumaas yung kanyang efficiency. So before we proceed to the lesson on actual Rankine cycle, we're going to discuss first all the methods that we may do or we may apply to increase the Rankine cycle efficiency. So our first method is to lowering the condenser pressure. So when you say lowering the condenser pressure, the colored area on this diagram represents increase in network output as a result of lowering the condenser pressure from P2 to P2 prime. So please take note that this P2 prime is the actual condensing pressure. Okay. So for the heat input requirements also increased, which is represented by the area under curve 4 prime to 4. But this increase is very small. So what do you mean by that? For your 4 prime, instead of 4 that we are on the ideal Rankine cycle, for we to be able to lower the condenser pressure, it deals more increase in W net or the work net. So if you can compare from the previous ideal Rankine cycle, this 1, 2, 3, and 4 and 1, this is the actual Rankine cycle, but if we're going to lower the condenser pressure, we will introduce A2 prime. So what do you mean by that? So when you lower the pressure, the condenser pressure, as you can see here at 2 prime, the point is on the inside of the saturated region. And then, as you can see, the line that goes to the 3 prime will become longer than the line from 2 to 3. So therefore, this line corresponds to the increase in work net. So this shaded region is the area that are increased in work net. Then after you have a 3 prime, therefore you have a 4 prime which correlated to those to 3 prime. And then for the 4 prime, you go back to your initial state or your QA. So therefore, your QA is here and your QR is here. Then your work ng pump is on the 4 prime, 3 prime to 4 prime, and then your work ng turbine is 1 to 2 prime. The overall effect of lowering the condenser pressure is an increase in efficiency. To take advantage of the increased efficiency at low pressures, the condensers of steam power plant usually operates well below the atmospheric pressure. So your P condenser cannot be lower than the saturation pressure corresponding to the temperature of the cooling medium. Lower condensing pressure creates the possibility of air leakages into the condenser. So tama naman nga yun. For in a lower condensing pressure increases the moisture content of the steam at the final stage of the turbine. So meaning, mas maganda kung mas malaki yung moisture content mo. Because since siya nga ay condenser, we turn the vapor from to liquid. So therefore, from quality, which is ang vapor is quality, and then yung liquid mo is moisture content, So it's better to increase, it is better to have a more moisture content rather than the quality in a condenser. So your lower pressure in condenser increases the moisture content of the steam at the final stages of the turbine. Presence of large quantities of moisture is highly undesirable in turbines because it decreases the turbine efficiency and erodes the turbine blade. For the superheat, next, another method is superheating the steam to high temperature. So kanina, we lower the condenser pressure because kapag nga nilower natin condensing pressure, mas madaming mako-convert yung condenser na liquid doon sa vapor. So mas madali siyang ma-heat ng boiler. Whereas dito naman, superheating the steam to high temperature, papataasin naman natin yung temperature pa versus doon sa given na superheated temperature. Average temperature at which heat is transferred to steam can be increased without increasing the boiler pressure by superheating the steam to high temperature. The colored area on the S diagram represents the increase in the network. The total area under the process curve 1 to 1 prime represents the incomplete or the in-heat input. The overall effect is an increase in thermal efficiency. Superheating of steam decreases the moisture content of the steam at the turbine exit 2 versus 2 prime. So you will, as you can observe in this diagram, so we have the original equation, we have the original diagram which is 4 to 1, 1 to 2, 2 to 3, 3 to 4. So by increasing the temperature at the superheated region, so we have your initial one would be your 1 prime. So we increase the temperature, we increase the heat in this region. So therefore, an increase in temperature will increase in pressure as well. So ibig sabihin, mas lalapit sa saturated line, vapor line natin, yung ating 2 prime. And then paglapit natin doon sa 2 prime, ay pagtaas naman ng ating vapor. Okay, temperature to which steam can be superheated is limited by metallurgical considerations. Presently, highest steam temperature allowed at the turbine inlet is about 620 degrees Celsius or about 1,150 degrees Fahrenheit. So the highest steam temperature allowed at the turbine inlet is 620. So ibig sabihin, yun di yung mga commercially available nating steam or yung steam blades, turbine blades pala, is desirable only for at least for the maximum of 620 degrees Celsius. So, we'll add higher than that, it may cause steering and may cause, what do you call this? A breakage of your turbine blades. Next, another method to increase your Rankine efficiency is to increasing the boiler pressure. So increasing the operating pressure of the boiler automatically raises the temperature at which boiling takes place. It raises the average temperature at which heat is transferred to the system and thus raises its cycle efficiency. So here, in increasing boiling pressure, we increase naman itong ating process 4 to 1. So from 4 to 1, we have 4 prime to 1 prime. Please take note that those primes are your methods or your accessories that you're going to have for you to increase your Rankine efficiency. So this is the actual. Ito yung sinasabi nating actual, itong mga prime. And itong mga original na value, 1, 4, 2, 3, 3, 2 is your ideal. 1 prime, 4 prime, 3 prime, 2 prime is your your actual parameters. So, ibig sabihin, sabi daw dito, increase the boiler air pressure, raises the temperature at which the boiling takes place. And if it reaches the temperature, if it reaches the, if it increases the boiler pressure, ano sabi ko sa inyo kanina, it will add on the superheating process. Therefore, your point 1 would increase. So, your superheating steam increases. Okay? So, ayun yun. Increasing the operating pressure of the temperature thermally raises the temperature at which boiling point takes place. It raises the average temperature at which heat is transferred to the steam and thus raises its cycle efficiency. For a fixed turbine inlet temperature, cycle shift to the left and the moisture content of steam at the turbine exit increases, which is undesirable, meteorological unsafe. It's undesirable superheat, which is meteorologically unsafe naman. Maximum moisture content at turbine exhaust is not allowed to exceed 12% or the quality of steam to fall below 88%. So why? Bakit daw kailangan natin that the moisture content at the turbine exhaust is not allowed to exceed 12%? Because kung magiging mas basa pa yung ipapasok mo na steam yung turbine, it may cause hammering. And that hammering is a phenomena wherein nagkakaroon ng water yung high pressured mo. And pag nagkaroon ng and then kapag siya ay patuloy pa rin na nagha-hammering, it's very dangerous, especially on your turbine or kahit hindi na sa turbine, sa mga pipeline, it's very dangerous na magkaroon siya ng water hammer. Kasi it may cause explosion or it may cause a breakage in the pipeline or in the turbine, or it may damage your turbine plate. The maximum steam temperature at turbine inlet is fixed by the materials used. The minimum temperature of heat rejection is fixed by the ambient condition. So, yun nga yun, ambient condition, which is your temperature of the surroundings or the condition of the surroundings. Minimum quality of steam at the turbine exhaust is fixed by turbine blade erosion. So, even the slightest steam that passes through the turbine blade, siya ay from time to time, as the time goes by, it will cause erosion. So, kailangan pa rin natin ng constant and regular preventive maintenance ng bawat equipment para maiwasan natin yung deterioration due to blade erosion. Maximum steam pressure at the turbine inlet also gets fixed. Okay? So meaning on how, so sa madalit sabi, to be able to increase your Rankine efficiency, you have 3 methods. You have to lower the condensing pressure for you to be able to have a longer work net. You have to increase the temperature at your superheated vapor for you to be able to increase the pressure. And then you're going to increase your boiler pressure for you to be able to increase your steam, superheated steam. So let's go to the next chapter, which is the deviation of actual vapor power cycles from idealized ones. So yung diniscuss natin kanina on how to increase your Rankine efficiency, dito natin ipapasok or dito natin i-apply. So the actual vapor cycle differs from the ideal Rankine cycle as illustrated in the figure as a result of irreversibilities in various components. So here in letter A, in figure A, this is a deviation of actual vapor cycle from the ideal Rankine cycle. Those dashed lines represents your actual cycle, and those solid lines represents your ideal cycle. Again, in our designing of power plants or other cycles, we are more focused on the idea or the actual cycle. Because yun talaga yung nangyayari sa tunay na buhay during our during the during the practical work. So yun talaga yung nangyayari, which is yung actual cycle. The ideal cycle only is just the basis or just the theoretical, which is yung basis talaga natin or your yun nga, tama, your theoretical talaga. But that necessarily mean that ayun yung masusunod na cycle or na output. Doon pa rin talaga tayo sa actual cycle. And your B is the effect of pump and turbine reversibilities on the Rankine cycle. So yung pump and turbine mo, since 1 to 2 na tayo, ito yung effect ng turbine. Mapapansin mo dito, sa 2 prime, maba yung dito. So therefore, nagkaroon siya ng increase in work net. So if ever nagkaroon siya ng increase ng work net, therefore, you can increase your Rankine efficiency. Fluid friction and heat loss to the surroundings are the two common sources of irreversibilities. Fluid friction causes pressure drops in the boiler condenser and the piping between various components. Heat loss from the steam to the surroundings as steam flows through various components. Of a particular importance are the irreversibilities occurring within the pump and the turbine. Now, for the turbine losses. For the turbine losses, during the expansion of steam in the turbine, there will be no heat transfer to the surroundings and the expansion of the expansion instead of being isentropic will be polytropic as shown in the figure. So yung process 1 to 2 natin is the isentropic expansion. So this is your ideal isentropic expansion. But due to turbine losses, ano may tinatawag ng turbine losses? So we have your frictional force, have your so we have your frictional loss, we have your mechanical loss. So yun yung turbine losses natin. So therefore, nagkakaroon tayo ngayon ng actual expansion. And your turbine efficiency would become H1 minus H2 all over H1 minus H2 prime. So we incorporate your H2 prime in your actual turbine efficiency. Now, for the pump loss naman, there are losses in the pump due to irreversibility and the process of compression is polytropic instead of isentropic as shown in the figure. So we have 3 to 4, figure 3 to 4, which is your isentropic compression, ideal isentropic compression. And your 3 to 4 prime is your actual compression. So ito talaga yung nangyayari natin due to pump losses. So ano pa ba yung mga pump losses natin? Di syempre, you have your frictional losses, your mechanical losses, etc. etc. So again, kaya nga compute din natin yung efficiency ng pump because nandun din yung losses. Di ba kung hindi naman maganda kung hindi naman maganda ang iyong pump, kahit gaano kaganda yung pinapasok mo na steam or pumapasok na liquid pala papunta sa boiler, hindi din siya ganoon ka-efficient. The same goes as your turbine. Even if your turbine efficiency is, even if your steam is very good, and then your turbine efficiency is low, you cannot produce a good or huge, enormous power, electricity. So, ganun lang yun. Now, we introduce now a turbo generator. So, what is the use of this turbo generator? Ideal work is the work done by the steam during a reversible adiabatic expansion process of the turbine. Indicated or actual fluid work or indicated work or work prime or your actual work is the work done by the steam during an irreversible adiabatic expansion or polytropic expansion process in the turbine. Your break work, which is your WB, is the work useful as such the available work at the engine shop. Combined work or your WK is the electrical energy available at the generator outlet. Now, for your thermal efficiencies, your ideal thermal efficiency is work net all over your efficiency, cycle efficiency. For your indicated thermal efficiency, you have your work indicated work all over your cycle efficiency. And then for your brake thermal efficiency, you have your work ng brake thermal efficiency all over your cycle efficiency. And for your combined thermal efficiency, you have your work ng combined thermal all over your cycle efficiency. For the steam rate, you have 360 over work pag ideal steam rate. Pag indicated, edi work, indicated work. Pag brake steam rate, edi brake work. And for your compressed steam rate, we have your combined work. Please take note that the efficiency is greater than your indicated efficiency. And your indicated efficiency is greater than your brake efficiency. And that your brake efficiency is greater than your combined thermal efficiency. So these cannot be interchanged. So please take note that when you're answering a problem that involves all those efficiency, you can double check or you can recheck whether your answer is correct if it follows this rule. That efficiency is greater than EI, that is greater than EB. That efficiency is greater than EI is greater than the brake efficiency, and that the brake efficiency is greater than your combined thermal efficiency. Now, for the engine efficiencies, so yun naman, engine naman. So, indicated engine efficiency, NI, ganun pa din. You have your indicated work all over your work. Work net. Brake engine efficiency, you have your brake work all over your work net. For your combined, you have your combined work all over your work net. And for your turbine engine, you have your brake work over your indicated work. And for your generator efficiency, you have your combined work all over your brake work. For the heat rate, the ideal heat rate is HR equals M times EC. Your indicated heat rate is MI times EC. Then your brake heat rate is MB times EC, and your combined heat rate is MK over EC. So ito lang dyan, ito lang din yun. Pinaghahalo-halo lang natin. So, nandiyan ito lang din yung dalawang ito. Okay, let's try to solve this problem. So, this problem is a Rankine turbo generator unit. So, a Rankine turbo generator unit receives 27,000 kg of steam at 1.2 megapascal and superheat by 122 degrees. Condensate leaves at 22 degrees Celsius. For a brake steam rate of 4.74 kg per kilowatts, mechanical efficiency of 90% and generator efficiency of 94%, we have to determine the ideal cycle thermal efficiency, indicated engine efficiency, and the condition of turbine actual exhaust and the turbo generator output in kilowatts. So first things first that we're going to do is to draw ATS diagram. So to draw ATS diagram, we have to analyze the problem. So we draw the ATS diagram. So, okay. Now, a turbo generated unit receives 27 kg of steam. So you have your steam rate at 1.2 megapascal and superheat by 122 degrees. So therefore, you have your superheated, which is 1.2 megapascal, that is superheated by 122 degrees. The condensate leaves at 22 degrees Celsius for a brake steam rate of 474. So, ibig sabihin, Lagay muna natin ito. Dito. Then, after nyan, draw muna tayo. Okay. Now, for you have your 1.2, which is your superheated pressure, and you have your 0. You have condensate leaves at 22 degrees Celsius. So meaning you have 1.2, sige, at point 1. So ano yung temperature natin sa point 1? Hahanapin natin. Ang sinabi lang kasi dito is 1.2 and superheated by 122 degrees. So at pressure equals 1.2 megapascal, we have a temperature which is equivalent to your Tsat, which is equal to, ano ba ang Tsat niya? Tsat plus your degree, superheat degree plus your degree superheat. Yeah, which is equivalent to, ano ba ang Tsat at 1.2? Punta sa table 2. Tsat at 1.2 is 188 degrees Celsius plus 122, which is equal to 310 degree Celsius. Kaya ito ay point 1 natin is 310 degree Celsius. Next, we have your point 2. Hanapin naman natin itong point na to. Your point 2, since sinabi is condensate leaves at T equals 22, so you have your temperature equals 22 degree Celsius. Your Psat, ano ba ang Psat natin pag 22 degrees Celsius? Punta sa table 1, which is equivalent to 0.00264 megapascal. Now, if you think that my discussion is very fast, you can pause my video or you can rewind para makasunod kayo. And then for your S, at point 2, we have 7.0692 kilojoule per kilogram Kelvin. Now, please take note, you compare this S, okay, to your SF, to your SG, and to your SG. Since S is greater than SF and less than your SG, therefore, at point 2, we can say that this is a wet mixture. Or sa madalit sabi, you are on the saturated region. So, we're on the right track. So, nandun talaga sa saturated region siya. So, therefore, hanapin natin ang SF. SF is equivalent to 0.3251 and your SFG is equal to 8.2979 kilojoule per kilogram. Now, we solve for the quality. Since siya ay pag siya ay nasa wet mixture, automatic we need to solve the quality. So, yun, S equals SF plus XSFG. So, hindi ko na inilagay. So, you have 3.3251, 0.3251 plus X times the quantity of 8.2979. So, your quality, which is equivalent, quality ng 0.2, is equivalent to 0.81274,78037, which is 81.274,78037%. Now, next, we find also the value of the H. Since siya ay wet mixture, kailangan din natin siya. So, your HF is 92.33. Your HFG is equal to 2449.4. So, therefore, your H2 would become HF plus XHFG. So, your 92.33 plus your 0.81 na quality. Please store sa calculator. Yun ang kailangan natin. Times 2449.4. So, therefore, your answer here is H2 2083.07447. Okay. So, we're going to delete first this. Ay, na-delete yung ano. We're going to delete ito para magkaroon naman tayo ng room for other solutions. So, you can pause it anytime, then you solve synchronously or together with my video. Okay. So, lagyan na at 310 degrees. Okay. Now, at point 3 tayo, at state point 3, ang tinada daw natin is 22 degrees Celsius kasi siya yung sa condenser na. So, therefore, your pressure is equal to 0.002645 megapascal. And then your HF, pick up lang kayo na pick up ng value. HF at 22 degrees Celsius is 92.33. And your VF is 0.00102 cubic meter per kilogram. Now, at state point 4, we find the H at state point 4. At state point 4, we have your H4 equals what work ng pump plus H3, which is equivalent to mali pala aking H4, kunin mo, wala pa pala tayong work ng pump. So by using these values, makuha natin yung work ng pump. Work ng pump is equivalent to VF times P4 minus P3. So therefore, your work ng pump is equal to 0.001022 times 120 kilopascal minus 2.645 kilopascal, which is this one, and yung 1 to na ito, this one. So therefore, you have an answer of 1.1998981 kilojoule per kilogram. Now, at state point 4 tayo. State point 4 naman, you have your H4, which is equivalent to your work ng pump plus your H3. So, may work ng pump na tayo, which is equivalent to 1.199989181 plus H3, which is 92.33, yung sinolve natin kanina, which is now equivalent to 93.52998918 kilojoule per kilogram. Now, for your letter A na hinahanap, determine the ideal cycle thermal efficiency. When say ideal cycle thermal efficiency, we have the EC, thermal efficiency, which is equivalent to W net all over your QA, which is equivalent, your W net is equal to QA minus H2 minus H3 all over, ano ba H2 minus H3? Ito yun. You have your QR, QA minus QR. Then you have all over QA, which is equal to 1 minus 2083.074 so on minus 92.33 divide all over, you have 3067.5 minus 93.5299 so on times 100%. So your efficiency is equivalent to 33.06104.43%. Okay? So for your letter B, we have the indicated engine efficiency. For the indicated engine efficiency, you have your brake work equals 36 all over your mass ng brake mass, which is equivalent to 36 all over 4.74. The brake steam rate of 4.74. So therefore, you have your brake work, which is equivalent to 759.493679. For your letter C, the condition of turbine. Brake, ang hinahanap pala is indicated engine efficiency. So di pa tayo tapos. This is only the work. So the general equation in finding the indicated efficiency is indicated efficiency equals, you have your indicated work all over your work ng turbine. So wala pa tayo indicated work, wala pa tayong work ng turbine. So we have to find first the indicated turbine. Indicated work is equivalent to your brake work all over your thermal efficiency. May ibinigay na term na mechanical efficiency, which is 0.90. Sorry, you have your brake. Pag brake, ang katambal niya is mechanical, hindi thermal. So you have your mechanical efficiency. So 759.49 so on divided by 0.9. So you have your indicated work, which is equivalent to 843.881.8565. So, meron na tayong check. Wala pa tayong, ngayon, makukuha na natin yung efficiency. So, your thermal efficiency, your indicated engine efficiency is equivalent to 843.8881.8565 divided by your work ng turbine, which is equivalent to 3067.5 minus 2083.07447 times 100, which is equivalent to 85.723.8034%. So that is your indicated engine efficiency, your NI, not your thermal efficiency. Okay, NI ito, TNT. Your NI, kasi ito ay indicated work. Okay, so burahin natin ito. Next one. For your letter C, condition of turbine actual exhaust. So therefore, meron na tayong actual exhaust, turbine. So ano ito ba? Ito yung 1 to 2. So nandito yung turbine. So magkakaroon tayo ngayon dito ng brake line, which is your 2 prime. So your actual exhaust, turbine actual exhaust, so your indicated pressure, which is equivalent to your mass flow rate, multiplied by your indicated work all over your 360, which is yung conversion. So we have 227,000 multiplied by 3067.5 minus H2 prime. Okay, minus 1.99981. Please take note, meron tayong prime para mahanap yung actual natin. Then, divided by 36. So therefore, you have H2 prime. Ano yung indicated pressure natin? Indicated pressure natin, ay mali. Mali pala, sorry. This is the value for let me check. Okay, so this is wrong. Di pala ito. So you're going for, hanapin muna natin yung PI kasi wala pala tayong PI. So your PI is equivalent to your mass flow rate over your indicated power. Your indicated work pala is 843. So mali ako ng kopya. So 843 yung indicated power mo. 843, sorry for that. 843.8818565. Okay, divided by 360. Divided by 3,600. So you have your PI which is equal to your indicated pressure which is 6329, and the indicated power 113,924 watts. Okay, and for you to be able to get the actual H na, kasi ito yung ideal natin. So you're going to itong indicated work natin dito sa turbine, yun yung papalitan na, yun yung itutulis natin ng H. So mangyayari will become 6329.113924 equals to 27,000 times, 'di ba itong indicated work natin sa turbine, may incorporate na natin yung H prime kasi yun hinahanap natin, the actual minus H2 prime minus 1.1998981 all over 36. So makukuha mo ngayon yung actual enthalpy niya, which is equivalent to 222.41814. We will see kung ito ay sa wet mixture pa rin since tayo ay na dito sa area ng saturated region. So if your HF is less than your H2 prime and your H2 prime is less than your HG, therefore siya ay wet mixture. So tingnan ninyo maigi kung siya ay wet mixture and you decide. So kung siya ay wet mixture, you're going to find the quality ng X. That quality ng X yun yung turbine exhaust. So we have 222.41 equals HF, which is equivalent to yung kinuha natin kanina na HF 92.33 plus X HFG 2499.1. Sorry, 2499.4, which your H2 prime is equivalent to 86.96, 36.7087%. And for the last, you have the turbo generator output in kilowatts. So for the turbo generator output in kilowatts, let's delete this one. We have the formula in getting the power, which is equal to PI, your indicated power, multiplied by your mechanical power, multiplied by your generator power. So your indicated power is 843, sorry, 843.881, sorry, 8565 multiplied by 0.9 multiplied by 0.94, and your power output of the turbo generator is 5354 0.430.3 8 kilowatts. 5354-4308-34 kilowatts. So that's it for your actual Rankine cycle. So if you have any questions with regards to this topic, you may feel free to contact me. I will be dropping on the description below my email address so you can contact me. So that's it for this video. I hope you learned a lot from me and I hope you follow the process on solving the actual Rankine cycle. Hope see you soon guys. Keep safe and God bless. Thank you.